not 0. And the value of the enthalpy of steam is 2501.6, is not 0. The value of liquid water is 0. So if that is the case, then your reference state, you get the temperature. Okay, this is your liquid water, your pressure and your temperature. But the state must be that of water, not of steam. Somehow, you guys got confused when the question stated that it is steam, you assume that your reference state will be steam. No, if you're using the steam table, your reference state must be liquid water, not steam. You cannot have steam because the enthalpy of steam at the triple point is not 0. So you got to make sure that you get the fact right, because the reference state is very important. Whenever you do energy calculation, energy balance calculation, you need to know where you start from, when it is 0. Because enthalpy is not something that you calculate directly. It's based on a difference from the reference state to the value that you wanted to get. So it has to be, your reference state must be well specified. You need to specify the state. In this case, for the steam table, is liquid water, and the temperature and the pressure. But if you don't want to write the temperature and the pressure, all you have to say is at triple point, liquid water at triple point. So here, liquid water is at triple point, but you still need to mention that it is liquid water. You need to mention that it is liquid water. You cannot say it's steam because enthalpy is not 0 for steam at that triple point. So please get it right, because I seem to come across this a few times when I was looking at your assignment. Somehow you got confused just because the question state that it is steam. The reference state depends on where you get your data from. If your data is from the steam table, then you refer to that of the steam table. It doesn't matter what the question is all about. Okay? It just depends on where you get your data from. Any question on that, please? Anybody? Is it clear? Guys? Am I talking to myself?
Clear, Doctor.
Good. Okay, I think most of you guys are not here yet. Only a few of you.
Doctor,
Yes.
I have a question. Like, what if we have like different gases other than steam, or like different gases? Like maybe another like methane or something else.
Okay, if you have methane, then your reference state will be that gas. If you're not using the steam table, don't get the reference point for steam table. Don't get the reference point for water. If it's for methane, then your reference state will be for that gas methane and where you get your data from. For example, I think I have, I stopped sharing this. Okay, I need to share you guys the appendix. Okay, let's look at one table, B8. I'm not sure what page is it. It's B8, table B8. Is this B8? No, it's B6. So that's B6. Still B6. Okay, B8. That's B8. Let me see. Am I sharing it? Yes, I'm sharing it with you guys. Okay, have a look. Let me use my pencil so that I can box my reference state. Here it is already specified. Reference state. Okay, your reference state. If you're using this table, B8, you have to follow that reference state. For example, you are looking at only, not all of these gases, you're looking only at, for example, carbon dioxide, just for carbon dioxide. So your reference state will be carbon dioxide gas, because all these are gases. So your reference state will be carbon dioxide gas at a pressure of 1 atm and a temperature of 25 degrees C. Why 25 degrees C? Because if you look at the temperature, the enthalpy are all 0 at that temperature. Okay, so that's why your reference state is at 25 degrees C, because the enthalpy are 0 at that temperature, at that pressure. For example, if you're using carbon dioxide, the question specified that carbon dioxide, then it will be carbon dioxide bracket gas at 1 atm at 25 degrees C. That's the reference state. Any other questions? Any other questions?
Yeah, I got it. But also for the, let's say, thermodynamics property table,
Mm-hmm.
is it okay to use it? Because in the previous assignment, like I was referring to some of them. Is it like okay?
You can use the data from thermodynamic textbook,
But
but you have to get
there's
the
a
reference
slide.
state, the steam table, you mean?
But there's like a slight difference, you know.
Yeah, very slight difference.
But it's okay, right? Like in the values.
The value should not be a problem because it's from the steam table, is tabulated values. I don't think it will make that much of a difference. I don't know why there is a difference because the data should be, close enough, not that big a difference. You can use the
Uh,
steam table from the thermodynamic textbook. Yes, you can.
all right, thank you.
Okay. Okay. Any other questions before we start our today lecture? Please remember that your basis must be the flow rate or the flow rate, either mass or volumetric or molar. Okay, so I did mention that we can use energy, but better not, don't use energy. Don't use energy. Use molar flow rate, mass flow rate, or volumetric flow rate. If it's not given, you need to calculate it. Whatever value you calculated, that will be your basis. Okay, so I'm going to stop sharing this. We're going to look at today's lecture. Okay, oh dear. I hope you can get the iPad. Hold on. Okay. Today's lecture is from chapter 8. I did mention something about, I did started a bit last week on hypothetical path. The reason you're going to do hypothetical path is that you need to calculate the enthalpy. You're not going to be able to get it from any data. In chapter 8, you need to know how to calculate your enthalpies. Okay, so whenever you whenever you want to calculate the enthalpy, you draw yourself a hypothetical path. I will show you guys how to do that, but you need to know the table, the what changes that is going to happen. From the changes that you have done step by step, you need to know how to get the enthalpy. Okay, let's look at this table. If you're dealing with ideal gas, we're going to assume ideal gas. You're going to deal with a temperature that is above 0 degrees Celsius, a pressure that is not too high, then you can assume ideal gas. So if you're looking at ideal gas, the enthalpy when there is a change in temperature at constant pressure, constant phase, this is constant phase, constant pressure. At constant temperature, you will calculate your enthalpy using that formula, the integration of Cp with respect to time. If you're looking at a closed system, this is an open system. This is a closed system. If you're looking at a closed system, you will be looking at delta internal energy, the change in internal energy. The difference between the two is that this is in constant pressure, this is constant volume. Okay? So if you're looking at closed system, you'll be integrating the heat capacity at constant volume. If you're looking at an open system, you'll be integrating it the heat capacity at constant pressure. That is when you're looking at gases. And when there is a change in pressure, but temperature and phase are constant, you only change the pressure, both the values of the enthalpies and the internal energy is equal to 0. You need to know this. This is for you to refer to. Okay? So when you're looking at liquid and solid, there's a bit different here. Your closed system, delta U is still the same, but for the open system, there's an additional term that you need to add to it, which is the specific volume times by the difference of the pressure difference. Okay? That's the term that you need to add to that integration. That is for liquid and solid. And when you're looking for the enthalpy change at a constant pressure, that's the specific volume times by the change in pressure. Right now, it doesn't, I mean, you just look at it, you don't know what's going on. So let me just explain first. After that, we do some example. And the internal energy, the change in internal energy is equal to 0. We just need to know this. Don't worry much about, don't need to memorize the equation. You just need to know what equation you need to use. Okay? But one thing I can say here is, whenever there is a change in temperature, okay, that's a change in temperature. Let me change in temperature. Whenever there is a change in temperature, you will calculate change in enthalpy is always integration. Change in internal energy is always integration from T1 to T2. You get your Cp with respect to time, temperature, Dt. Same here, T1, T2, Cp, sorry, not Cp, Cv, not P. With respect to temperature, Dt. Okay, that's the easiest one to remember. The rest, you need to just look at the table. But every time there is a change in temperature, then you will need to integrate. Your value of Cp and Cv, either it is given, or you can look it up in the appendix, or normally it's given. Okay, your Cp is normally given, or you look it up in the appendix. Okay, let's look at. Let me see. Where is the Cp's? Okay, your Cp is normally in a polynomial form. This is at the back of the appendix. I'm not sure whether you come across this before in thermodynamic. Have you guys come across this? Cp in polynomial form. Yes, so it's nothing new. Okay, so it's available in the appendix. So nothing new. Okay, how do you connect between Cp and Cv? For ideal gases, this is the equation. This is nothing new. It's in thermo. Cp is equal to Cv plus the gas constant. And if it's liquid and gas and solid, sorry, Cp is approximately equals to Cv. So that you have come across this, nothing new. Okay. So let's look at our appendix. This is the appendix. This is appendix B2. Let me zoom up. Okay, this is appendix B2 in your textbook. That's B2. Right. Let me use, for example, take note. This is form 1. Take note of the form. Right? Take note of the form. This form 1 is in the form of A, B, C, D. Form 2 is in the form of A, B, C. And the power is different. Okay? Please take note of that. There's two types of equation. Form the first and the second. There's a difference in the polynomial equation. So you need to look at, for example, you're looking at acetone. If you're looking at acetone, you'll be looking at form 1. That is form 1. So that is form 1. A, B, C, D. Okay. But if, for example, you're looking at calcium carbide, you'll be using equation 2, which is the second form of the equation of the polynomial equation. So please take a look. Please, before you write anything else, look at the form, because I come across students that assume that all the substances is going to be in the form of form 1, which is the first equation. No, some of them do not use the first equation. Some of them use the second equation. So please have a look before you start writing your equation. And another thing that you need to look at is whether it's liquid or whether it's gas. Okay, because sometimes it can also occur in the form of solid. C is crystal. So bear in mind, when you're looking at the appendix, you need to look at the form, what equation you're going to use. Is it the first equation or the second equation? And also another thing, look at the temperature unit. Is it in Kelvin or is it in degree C? Yeah, are you going to use Kelvin or degree C? So whenever you integrate, for example, you're using degree C, then your integration will be, the temperature will be in degree C. If you're integrating using Kelvin, then your temperature will be in Kelvin. So you need to take note of that. Okay, so please, whenever you look at the appendix, have a look at the form, the state, and the temperature, the unit of the temperature before you start writing your writing your equation and before you start calculating. That's one thing I need to point out. Okay, let's see whether I have a question. Let's see. Let's look at this is heat capacity, example of heat capacity. Let me look at this one. This example. The notes that I have now, the slide that I'm showing you guys is already in e-learning. I'm not sure whether you guys already download it or not, but the notes are already in e-learning. So have a look at this example. You have a liquid change from 25 to 125 at 1 atm to 100 at 5 atm. So there's two type of changes going on here. There's the temperature change, right? There's the temperature change from 25 to 100, and there's the pressure change from 1 to 5 atm. So if the CP is given, you don't need to look it up. The CP is given. So now, before we can do this calculation, you don't have any, the data is not given for this liquid. There's no mention at all of what type of liquid it is. You're not going to look it up in any appendix because you don't even know what type of liquid it is. Okay, it's just a liquid. Right? So what you have to do is you have to come up with a hypothetical path. So we're going to start from 25 degrees C, this liquid, write down it is a liquid at 1 atm. You're going to go to 100 degrees C, still liquid, no change of phase, still liquid, but a change of temperature and pressure. So what you start this here, you will denote that as your enthalpy 1, and your specific enthalpy 1. Yeah, this is going to be your final enthalpy 2. So what you have to do is you need to go from 25 to 100. So you're going to increase your temperature, still liquid. You did not change anything, still liquid, but you change the temperature. You are still at 1 atm. You cannot change both of them at the same time. Either you change the temperature or change the pressure. Either one. You cannot change both. Okay? So this is a change of temperature. So just write the change of temperature. Now you already got 100. Your final state is 100. You just need to change to 5 atm. So this is going to be a change of pressure. So now your overall enthalpy change is going to be delta enthalpy 1 is for the first step, which is the change of temperature, and the delta change enthalpy change for the second one, which is the change in pressure. So this is going to be delta H1 plus delta H specific enthalpy change 2. Okay, so the overall is going to be that. Now, H1, H2. You're going to find H2. For example, if you're already going to find H2, then H1, you're going to give it as your reference state. So this is going to be your reference state. Why is it a reference state? Because you already specified that your enthalpy, let me undo that. Because I overlap on the, okay. This is your reference state. Why is it your reference state? That's your reference state. Why is it your reference state? Because your enthalpy is 0 at that condition. At that condition, your enthalpy is 0. So that is your reference state. So now, what actually you are doing, your overall H is actually H2, your specific enthalpy, minus H enthalpy of 1. But you already said that your reference state is going to be at condition number 1. So this is going to be 0, and that is going to be your enthalpy at condition 2, your final condition. I'm going to denote final condition as 2, initial condition as 1. So this is actually what you are doing. You are calculating the enthalpy at the second condition, the final condition. So this is what you're doing. Okay, now I need to look back at the change in temperature. Go back to our notes. Here. Just now the this table. I'm going to clean this up. Ouch. Okay. You already wrote down just now the example. Let's look at the example just now. Where this is the example. We have a change delta. Oops. Oh dear. Yeah, we have a change of temperature. For the first step, a change of temperature. We have the change in temperature. This is a change of temperature. So let's look at the change in temperature in our table. What are we dealing at? What substance are we looking at? Is it liquid? Is it gas? Is it solid?
Liquid.
Liquid. Okay, so we're looking at liquid. So it's a change of what?
Temperature and pressure.
Temperature. No, the first step.
Temperature.
Temperature. Okay, change in temperature. It's liquid. We're going to look at enthalpy because I was calculating enthalpy. So we should be looking at that equation. Is it?
Doctor, this will pressure.
Yes, I just wanted you to be alert. Okay, so that's not it. So it should be this. The change in temperature. Constant pressure. You keep the pressure constant. Let's have a look. Where is that example just now? Yeah, the first step. You're going to calculate change delta H specific enthalpy 1. It's a change of temperature. Where's the pressure? 180 M. Where's the pressure? 180 M. So the pressure is constant. The liquid is also still constant. You do not change anything from liquid to vapor. No. It's still liquid. So there's no change of phase. So let's look at the table again. Where is my notes? Okay. We are looking at constant pressure, constant phase. Only change in temperature. There's only change in temperature. So this is the equation you're going to use. Write down the equation because we're going to use the equation. Let me get. Okay, now let's go back to that example just now. Okay. We're going to calculate delta H1, change in temperature. Oops. Okay, so our delta H, oops, undo that. I should be using my pen. Okay, delta H1 it involves a change in temperature. So the equation that we just got from the table just now, we're going to write it down. T1, T2, Cp of your liquid. We don't know what liquid it is. dt. Okay? Now, let's go back to that question. The Cp is given. The Cp is given over here. And what is the temperature of T1? Somebody. You're going to integrate from T1 to T2. What is the temperature of T1?
25.
25. Yes, that is T1. And T2 is going to be 100. Starting point is T1. T2 is your final point. Or final, so not final. T1 is where you start your temperature. T2 is where you end your temperature. Okay, for this case, for the first step, which is delta H1. So let's go back. Okay, so T1 is equal to 25 degrees C. T2 is 25 degrees C. Now sorry, I should not have 100. I should not have 25. I should have 100 degrees C. Okay, what is the Cp? Let's go back to the equation. Cp is in terms of degrees C. That's why we write our integration degrees C. So let's jot down that equation. I need to write that delta P plus 25. I hope you guys know how to use your calculator to integrate. I'm going to write down the equation. Let me see, where's my equation? 0.103 plus 1.39 times 10 to the power of minus 5 T bracket dt. Okay, let's look. That is the equation. Okay. Minus 5 times 10 to the power of minus 5. That's what I did. Okay, now, let's go back again to our hypothetical path. From liquid at 25 degrees C, 180 M, you go to liquid at 100 degrees C, 180 M. What changed? Anybody? Anybody?
Again, doctor?
From liquid at a temperature of 25 and a pressure 1 atm, going to liquid at a temperature of 100 degrees C, 1 atm. What changes?
Of course, temperature.
Pressure.
Temperature. What about the pressure?
Pressure.
Constant.
Constant.
It's constant. Okay, so if the pressure is constant, what will happen to delta P here?
0.
0. That will be 0. Yeah, you end up only one equation over here, one integration. So can somebody get me the answer? Use your calculator. You should know how to do this using the calculator. Give me the answer, and I will also try to get it myself. Ouch. You need to use integration. If you don't know how to use how to integrate using your calculator, that's you need to know how to do it, because this is you're going to do a lot of it.
Is it 7.725?
Sorry?
7.725.
7.725. What is the unit? Go back to the equation. What is the unit? The unit is kilojoules per mole. You already cancel the temperature. It's going to be kilojoules per mole. So this is going to be kilojoules per mole. Anybody get a different value? Is that the same for everyone? Somebody? Let me get my finish my calculation. See whether I can get the same. Ouch. I get 7.726. Very close.
This is, I got the same.
Same, 7.725. Good. Okay, now for the second step. Let's go back. The second step, which is that enthalpy change, it involves change in pressure. Only pressure change. Why? Because when you start, you are at 1 atm, you end up at 5 atm. Yeah, you end up with 5 atm. Initially, you are at 1 atm. Your temperature is the same. So it's only a change of pressure. So let's go back to our notes, to our table. Now, which one are we looking now? What are we looking now? Is it change of temperature or is it change of pressure?
Change of pressure.
Change of pressure. What state are you looking at? Liquid, solid, gas?
Liquid.
Liquid. Okay, so this is your change in enthalpy. Change in enthalpy. Now you're looking at a change of pressure at constant temperature, at constant phase. Okay, let's look at the example. Your liquid is still at the starting point is, let me circle this, that's liquid, and you finish and you end up as liquid. Your temperature, 100 degrees C, your temperature is also 100 degrees C. The only thing that changed is your pressure from 1 atm to 5 atm. Your state, your phase is still the same. Your temperature is still the same. No change in phase, no change in temperature. It's only the pressure. So let's look again at that table. Okay, so constant temperature, constant phase. Only a change of pressure. So this is the equation that you need to write down for that second step. For the first step, we already done that. We got this equation for the first step that we did just now. This is what we got just now. Now, for the second step, the change in the enthalpy for the second step, we need to write that equation. So let's go back to our example. We are going to write down the equation. Change in specific enthalpy, specific volume, change in pressure. Okay. Pressure change is from 1 atm to 5 atm. Let's look at the question. We are given density. We are given the molecular weight of the liquid. Density is equal to 1 over specific volume. So you already get that. So that means specific volume is equal to 1 over density. Okay. Okay, let's go back. Your pressure change, let's write down the value. Okay, that's 0.873. 1 0.873, jot down the unit. gram centimeter cubic. Yeah. Your pressure change, the final pressure minus the initial pressure. So that's 5 minus 1. The unit is in ATM. Okay. We need to get these two change in enthalpy having the same unit, or else you cannot add it up. So you need to change the second enthalpy to kilojoules per mole. So what you can do is, you go back to that question just now, you are given the molecular weight. There is the mole there. Okay, so that you can cancel the gram. Alright, so now we have the gram there. So what is the molecular weight? Is 48 gram per mole. Okay, cancel off the gram, but you still got centimeter cubic, 1 atm. So if you look at the equation that I have over here, I have this constant here. Okay, you need to use the gas constant as your conversion factor. Remember when we did the first chapter 7, we used the gas constant as a conversion factor. So I need to change from ATM, I need to cancel off the ATM. Here I have ATM, there I have ATM. But my pressure, this is not ATM, sorry. Not the second one, not that one. Okay, there's one ATM, there's ATM, there's one ATM. Okay, but I'm not going to use this equation. I'm not going to use this equation because that's in English unit. So I'm going to use the first equation, the first gas constant, which is that gas constant. I'm going to use that gas constant to as my conversion factor. So let's go back to this. I'm going to cancel ATM, so I'm going to use 0.08206 liter ATM per mole per Kelvin. Okay, I can cancel the ATM, and I need to cancel, I need to bring it over here. I need to cancel the liter, the kilo centimeter cubic and the liter. If you look at your conversion factor at the front page of your textbook, one liter, how are we going to get it? 10, I'm going to change centimeter first. Centimeter to 1 meter cubic first. Okay, so that I can cancel this. Use your conversion factor from the front page. And then from 1 meter cubic, I'm going to change to liter. So I'm going to cancel the liter. I'm going to cancel the meter cubic. So now I have left, what do I have? Mole, cancel mole. Still, I don't have the unit that I want, which is kilojoules per mole. So what I have to do is, just now I got that gas constant, I need to get another gas constant. I need to get another gas constant so that I will get joules. I need to get that joules there in order to get kilojoules per mole. So let me erase that. Okay, I need to use that. Is there any other unit that have joules? No, that's the only gas that have joules. So I need to use that gas constant together with the one at the top here, because these two gas constant will become my conversion factors. Okay, so now let's go back to my equation. Oops. So I need to cancel the Kelvin there. So I'm going to write my gas constant at the numerator. Joules, mole, Kelvin. Okay, so I can cancel my joule, my Kelvin, but still not the same unit. I need to change my joules to kilojoules. 10 to the power of 3 joules, 1 kilojoules. So now I'm going to have the same unit as the one I have calculated for my change in step 1. Change in enthalpy step 1. So somebody calculate it, please. What is the answer? Somebody please give me an answer. What I can see over here, 10 to the power of 3 cancel, 10 to the power of 3, 10 to the power of 3 cancel.
Doctor,
Yes,
I got 0.022.
0.022.
Yes.
Thank you. Because it's very small. Normally, the specific volume is very small. So whatever change of pressure change that is going to occur will also turn out to be small. If you look at your specific volume here, it's very small. Once you convert it to, for example, meter cubic per kilogram, it's going to be very small. So whatever changes that happen with the pressure will also end up being small because your specific volume is small. Anybody get a different value? Okay, now let's go back to the question. What is the question? Calculate the change in enthalpy. So the change in enthalpy is this, delta H overall. Your delta H overall, that's overall. Okay, delta H overall. Sorry, that is not, I need to cancel that. Okay, that is delta H overall. That is delta H overall. This is delta H overall. Right? So delta H overall, if we write the equation, is equal to delta H1 plus delta H2. So when you add it up, you have 7.725 plus 0.022, and your final answer will be, it should be 7.747, is it? I'm using mental arithmetic here. Is that the answer?
That's right.
Yep, that's the overall change. Let's check the answer given. Oh, 7.81. Why are we not getting 7.8? Why are we getting 7.725? 7.75. Round it off to 7.75. Oh, the answer given is 7.81. There might be slight change in rounding off error, maybe. But it's about, this is the final answer. Oh,
For the change in enthalpy 1, I got 7.79. Not
okay.
7.72.
This answer is actually, let me erase. Somebody say is 7.7 what?
7.79.
7.79.
Yes, same doctor, 7.79.
Okay, I think that's where our mistakes, the addition up. Let's cancel this. 7.79. 7.79. So final answer is going to be
7.812.
7.812. That's the final answer. Okay, exactly like the given answer in the question. So what are we doing here? Actually, this is equals to your second enthalpy, specific enthalpy for the second state. Why I said so? Because we already specified that your first enthalpy is equal to 0. That's equals to 0. So actually what you are doing is you are calculating the enthalpy, specific enthalpy at the second condition. You can do this in reverse if you like. You can say the specific enthalpy at 0, at second is 0. So then your reference state will be at that condition at the second condition, which is liquid, 100 degrees C and 5 atm. If you change it this way, if you do the reverse, then your answer will be negative. That's the only difference. Now we get positive. Our answer is 7.812. But if you change your reference state, instead of 1 being the first position being your reference state, now you decide to select the second condition as your reference state, then the value that you will get will be negative 7.81 instead of positive. That's the only difference. Okay, guys? Do you get what I'm trying to say here? Anybody?
Yes, doctor.
Yeah, good. So what happened here is that your delta H overall, if you're using this, your answer will be negative 7.812 kilojoules per mole. That's a difference because you change your reference state. Initially, we did our reference state is this. That is our reference state. We have it at the first condition. Now, if you change it to the second condition, so what you are doing then is calculating for the enthalpy, specific enthalpy change for the first condition. If you selected your second enthalpy to be your reference state, this is H2, then you are calculating H1. But if you already specified that this is 0, then you're calculating H2. And that's what you're doing actually when you draw the hypothetical path. Any question, anybody? Anything that you find still confusing? Anybody? What we are doing here, we are using the gas constant to convert the unit. So what we did is we convert the unit. Whenever you deal with V delta P, you have to do conversion. Any questions, guys? Any questions?
No question, no sir.
Good. I hope everybody also no question, because somehow I seem to get only just a few that normally responses. Every time we have lecture, only these few that responses, that responds. The other just keep quiet. So I have no idea whether you understand or you
Yes,
don't understand.
doctor understand.
Good. Agatian. Good. So if there's no question on that, let's look at another example. Let me see. I want to have another example. Let's see. Is this the example? Okay. This is one good example. Okay, you're going to get the spec. Let me use this. Going to need specific enthalpy. The unit is kilojoules. You're looking at N-hexane vapor at 200 to atm. But relative, what does relative mean? That means you are using the sec relative to liquid hexane at 20 degrees C 1 atm. What does that mean? Relative to N-hexane liquid.
This is my
Reference
state.
point.
Which one is your reference state?
The liquid hexane at 20.
Okay. So your reference state is going to be this. Why? Because it's relative to. So that is going to be your reference state. Let me rewrite that. That is going to be your reference state. Yeah. So you're going to calculate the enthalpy of the second condition. Let this be your first condition, maybe. Or if you don't want to use symbol, it doesn't matter, but I prefer to use symbol. Okay, so now, assuming that is an ideal gas, you're going to assume ideal gas. So let's look at our appendix. Yeah, let's look at appendix. We are looking at N-hexane. Where is N-hexane? There is N-hexane. Let's use my marker. That's N-hexane. You going the symbol, that's the symbol. Yeah, that's N-hexane. This is the molecular weight. You have liquid and gas here. Yeah, you're going to use equation number 1. You remember that equation just now I mentioned. You're going to use degrees Celsius as your unit. Yeah. So you have two equation over here. One for gas and one for liquid. So why are we using two equations? Because you have vapor and you have liquid. So let's draw the hypothetical path first. You start with liquid. Why you start with liquid? Because that is your reference state. Yeah, you start with N-hexane. Oops. Let's change that. You start with the symbol. I need to use symbol. It will be shorter if I write the symbol. It is C6H14. I start with liquid. Okay. My temperature is 20 degrees C and 1 atm. Since this is my starting point, I said that is my reference state. So that is going to be, I give you a symbol of 1, 0. That's where my reference state is. So I'm going to change it to C6, same N-hexane, but now it's vapor. Yeah, I'm looking at vapor at 200 degrees C at 2 atm. I need to change from that to that. From the first condition to the second condition. So this is what is required. The specific enthalpy at the second condition, the unit will be in kilojoules per mole. Oops. Sorry, guys. Okay. Kilojoules per mole. So what I have to do is I've got to draw myself my hypothetical path. Okay. First step. What do I need to change? Anybody?
Change the temperature, please.
Temperature. Okay. Before that, I need to point this out. Yeah, I need to point this out. You have N-hexane over here. Yeah. We are changing from liquid to vapor, right? So if you're if you're going to change from liquid to, you need to boil it first. So the boiling point is 68.74. That's the boiling point. 1 atm. This is from table B1. The polynomial equation just now is B2. This is B2. Oops. I need to undo that. I need to write B2. That is B2, table B2. Yeah. From table B1, you get the information that is for the boiling point, that's the boiling point, at 1 atm. The boiling point is at 1 atm. And what you get from that same table is the enthalpy change for vaporizing it, for boiling it. That is the enthalpy change. If you look at this, there's a subscript V there. There's a subscript V there. That's V. That is the enthalpy change for vaporization. The unit is kilojoules per mole. So this is the enthalpy change when you are boiling it at 1 atm at its boiling point. This is the boiling point. Okay, so now let's go back. Okay, the question said that you're going to start from liquid at 20 degrees C, 1 atm. You're going to end up as vapor at 200 degrees C, 2 atm. What you have to do is you got to change the phase also. Instead of just temperature change, pressure change, you need to change it from liquid to vapor. So now you involve three things that need to be changed. Okay? And bear in mind that it has to be done, the change of phase from liquid to vapor must be at its boiling point at 1 atm. Because that is the way your data for your specific enthalpy change is available for the enthalpy change at vaporization. Okay? So what do you have to do next? Starting point, 20 degrees C, 1 atm. What do you need to do? Anybody? Anybody?
Change the temperature to the boiling.
Same temperature to what?
The boiling point, the liquid, the state the same, or the phase the same, pressure the same, temperature of boiling.
Okay, now the temperature of boiling is 68.74. Yeah, I'm going to go to still the same liquid. At the boiling point just now is 68.74 degrees C, okay, and 1 atm. Okay, now I'm boiling it. From there, I need to erase this first. I don't need it. I need it to be lower. Yeah, guys. I need to, because there's more changes that need to be done. Yeah, it's liquid at 68.74 degrees C, 1 atm. Okay, that is your change when you're looking at liquid at its boiling point, which is 68.74. Next, what else? What next?
Change the phase at constant temperature and pressure.
Okay, change phase, which is same temperature, same phase. Not same phase, vapor. Now it's vapor. It's same temperature, 68.74 degrees C and 1 atm. Still the same. Okay, now let's jot this down. This is change in temperature, which is delta H1. This is delta H2, specific change 2, which is equal to your change in vaporization, subscript V, which you can get from the appendix. Just now, what did we get? Yeah, if I zoom this up, that is the delta H vaporization at its boiling point, 28.85. So I'm going to write that value, 28.85 kilojoules per mole. Huh? Now, what else? What else? I haven't reached my final condition yet. What do I need to do?
Change in temperature at constant pressure.
Okay, change in temperature. So I'm already vapor. So I skip the vapor phase. Then change to the temperature. What temperature?
200 degrees centigrade.
Okay, 200 degrees Celsius and constant pressure, 1 atm. Next. What else?
Change in pressure at constant temperature.
Okay, that will end up with the final condition. So now let's give it this is the change in temperature. This is change in pressure. That is enthalpy change number 3. That is enthalpy change in number 4. So your overall change, your overall enthalpy overall is going to be the sum of these changes. 1, 2, 3, and 4. Yeah, the specific enthalpy change, my specific enthalpy change for these changes. Okay, now Remember I mentioned you guys, whenever you have a change in temperature, the equation is going to be very easy. Whether it's gas or liquid or solid. So let's go back to the first look at for the first step. Enthalpy change 1 is going to be change in temperature. What changes from liquid to liquid? Just temperature, liquid. So let's go back to our table. Where is my table? Okay. I need to erase this first. Ouch. Okay. Hey guys. What are we looking at now? What do we need to find? What do we need to find? Yes?
We're gonna use V delta P plus the integration of Cp delta T. The one for liquid at constant pressure.
Okay.
Pressure.
We are going to use liquid, that equation, is it?
Yes.
Okay, let's write that for our example. Where is that example just now? Here it is. Okay, that is going to be our change in this equation plus the integration. What is your first temperature? Where do you start from? What's the integration? The first temperature?
20 degrees.
20. Okay, we're going to write degree C. We're going to check later on whether the unit is 10 in degree C. Your final temperature is 68.7. That's your final temperature, degree C. And your Cp is going to be Cp of hexane, 17, that's 14, liquid Dt. Okay, that's the equation. For the third step, the second step we know is a change of phase. We already have the value for your delta enthalpy change. How about this?
The
How
third,
about this one?
same but without del P, V delta P.
Okay, let's go check on that. We are looking at what?
Vapor.
Vapor. Okay, we're going to assume ideal gas. Yeah, and we're going to use the equation. Yeah, so let's go back. This is going to be, I'm going to erase it. Okay. That is going to be from what temperature to what temperature?
68.74 to 200.
Okay, you start from the temperature where you start, 74 degrees C. Your final temperature, 200 degrees C. Now I'm going to write this vapor dt. Why vapor? Because you're already in the vapor phase. Okay. Now, how about delta H4? A change of pressure.
Equal to
For
0.
vapor. Okay, let's check. I have this table. Vapor, change of pressure, that's equal to 0. You keep the temperature constant, the phase is still constant, your enthalpy is going to be 0. So let's go back. For example, this is equal to 0. So now you have to do 2 integration. But before that, before you do your integration, let's look at this part. What's going to happen to that part?
Cancel it.
Why?
Because del P is constant.
Okay, because your pressure, delta P is equal to 0. Okay, you are starting at 1 atm, you end up also at the same pressure. So it's going to be 0. So you have 2 integration that you need to do. Now let's check our equation. Just now we have liquid. This is for liquid. This is for liquid. That is liquid. This is for liquid. Okay, that's liquid. That's for vapor. So let's check for N-hexane. Yeah, N-hexane. That's liquid. That's the unit for your temperature. We use degree C. We're going to use the first equation. The first equation, if I write down over here, Cp is equal to A plus Bt plus Ct squared plus dt to the power of 3. Okay, now let's look at this. I wanted A. This is A times 10 to the power of 3. If is equal to A times 10 to the power of 3. So what is A? What I'm going to substitute for A there? For this? What I'm going to trip for A? What is the value of A?
163 and
Sorry?
then 2 point.
Please. Arif?
Yes, betul.
What did you just say?
We should put the value 2.163 and then 4 5.
216 point, Arif.
Oh,
There's no point. Times 10 to the power of
3.
3. Okay. Is it going to be 3 or negative 3? Bring this over to that side because you wanted on the A. So it should be 10 to the power of negative 3 or 3? Guys?
Negative 3.
Negative 3. It should be negative 3. Same thing. If I wanted to let me say this is equals to, let's look, B times 10 to the power 5. B times 10 to the power 5. So if I'm going to write B for this part, B there, what B should be? B should be what? What is B? Somebody? What is B?
40.85
40.85. Then that's it?
times 10 to the 5
No, minus 5.
minus 5.
Yeah, it has to be minus. So please bear in mind, though it is written over here times 10 to the power of 5 times 10 to the power of 3 times 10 to the power of 8 times 10 to the power of 12. When you write it inside your equation, it should be times 10 to the power of negative, whatever there is. For example here, times 10 to the power of negative 5, times 10 to the power of negative 8, times 10 to the power of negative 12. When you write it inside the equation. So now, let me erase this because I need to tidy it up. Yeah. Yeah. Now we are looking at liquid. We're looking at liquid, there's only one. That is your only one value. So if we write that, I'm going to write it somewhere here. Letter H1. That I'm writing it all over again. Is equals to from 20 degrees C to 68.74. What is that just now? The value of A just now? 200. I can't see it. Where is it? 216.3. Remember my sign, my times 10 to the power of negative 3 dt. Why only one A? Why not B? Where is the B? Where is the C? Because it's stated if you're going to this only one value. There's no B, there's no C, there's no D. Right? So it's only one value of 216.3. That's your A. And remember, this is times 10 to the power of 3. So this is times 10 to the power of 3. When you do it, when you write it in the equation, it's going to be negative 3. So if you do this calculation, you should know how to do this because you have your calculator. But if you don't have your calculator, this is very straightforward. 68.74 minus 20. So what's the answer? I did this calculation earlier. I managed to get 10.542 kilojoules per mole. How do I know what unit I'm going to use? Let's look at the table. Oh dear. Just now the I need to go back. Not this table. I need to go back to our notes. Yeah. Yeah. This is the one that I need. This is the unit of your CP. Kilojoules per mole per degree C. So if you already multiply, do the integration, your final unit will be kilojoules per mole. So let's go back to my table in case I need it later on. Yeah, let's go back to that example. Yeah.
Doctor,
Yes.
why we typed it as times 10 to the negative 3, not times
Okay.
10 to the 3?
Okay, let's go back again to this. Yeah, I need to erase this so that you can see what's going on. Yeah. This whole thing, A times 10 to the power 3 is equal to that. Isn't it? Right?
Yes.
Okay, so if I write it here, A times 10 to the power of 3 is equal to 216.3. So if I want A, because I only need A, isn't it? I don't want times 10 to the power of 3. A is equal to 216.3. This thing, bring it over to that side. That means you divided it. Okay? Times 10 to the power of negative 3. Isn't it?
Clear the
Yeah.
yes.
Okay, good.
Thank you.
Welcome. So now, let's. Did you guys get this same value that I just brought here? 10.542. Did you check, guys?
Yes. It's
Good.
right.
Good. Thank you very much. So next, our delta H2 is already given here, but I'm still going to write it here. Our change in the second step is equal to 28. That is the change in phase, whereby you vaporize the liquid to vapor. That value, the start I mentioned just now, that value is given in appendix B1. That is the value when the change in enthalpy for vaporization. If, okay, now let's look at this. What are we doing? We are going from liquid to vapor. For example, if I go the other way, the other direction, from vapor to liquid, what is going to be my delta H now? What is it going to be? Instead of from liquid, now, initially I go from liquid to vapor. If I started from vapor to liquid, what will be my change in enthalpy? Anybody?
Well, it should be negative, right?
Yes, you got it. Thank you, Sulaiman. That should be negative because you're going from vapor to liquid. Okay, but we are going from liquid to vapor, so we stick with the positive sign, 28.85. Okay, so bear that in mind. So that's the second change in enthalpy. The change in enthalpy is that which is the integration. We already said that it should be integrated for the vapor from 68. We are looking at this from 68 to 200. Okay, 68.74 degrees C to 200 degrees C. Now we're going to integrate it for vapor. We are looking at vapor. So now let's look at the table again. We're going to use gas. Okay, I'm going to clean it up, tidy it up, because we're going to use only we're going to look at the value of A, B, C, D. Okay. So let me use my, this is A, this is B, this is C, this is D. But remember again, that is times 10 power 10 to 8, 10 to 5, 10 to 3. So I'm going to change it to negative, times 10 power negative. So let's just jot down that because I need to write it down. I'm going to write it down over here. That is going to be 37.4. Is it 37? 137. Sorry, guys, 137. 137. Let me erase that. 137.44 times 10 to the power of negative 3. Why? Because of the, just now I already explained why. The part B, the value for B is 40.85. Where is B? That is B. This is A, this is B, this is C, this is D. But remember, all of them need to be changed to 10 times to the power negative, negative, negative. Okay? So let's write down inside our polynomial equation times 10 to the power of negative 5. This is BT. Your CT. No, I'm sorry, I need to minus. Oops. Oh dear. Minus 23.92 times 10 to the power of negative 8 T square. And lastly for D, 557.66 times 10 to the power of minus 12 T to the power of 3 dt. Okay, bracket it. Now let's check. This is my A, that's my A, that's my A, that's my B, my C, that's my D. So where is my C? I wrote down here negative 23.92. My D 57.66. So that's what I just wrote down based on the table appendix B2. I just need to add up that part times 10 power negative times 10 power negative times 10 power negative times 10 power negative. Do not just get down that value in the table. Remember to put times 10 to the power of negative 3 times 10 power negative 5, negative 8, negative 12. Okay, now do the integration. What did you get?
24.66.
24.66. The unit again, same kilojoules per mole. So now let's go back to our chart. We already get delta H1, delta H2, delta H3, delta H4. So everything is there? No, delta H4 we haven't got it yet. Delta H4, we need to do delta H4. And what is delta H4? 0. Delta H4 is 0. Is 0. Why 0? Because we look at that table, a change of pressure. A change of pressure. Oops. Okay, a change of pressure. For other gases, a change of pressure, enthalpy change will be 0. This is it. We look at the table. So now everything is there. We already get all the values that we need. Your overall enthalpy change is equals to...
Doctor,
sorry? Yes?
I have a question.
Yes, please.
Between the B and C, the values, and delta H3, why you put a negative sign?
Again, the same question. I just answered that just now. I have to repeat myself all over again. Why? Okay. Same question. Okay. Okay. Let's see. This is equals that. This is equals that. This is equals that. And that is equals to that. Okay? But the equation that we're going to use, is in this form. That's the equation. Okay? Omar? That's the equation we're going to use, CP.
Yes, doctor.
Okay. So now let's look at just A. Just A. Just look at A. Just look at A. Okay? So what is the A for the gas? What's the value of A for gas?
137.44.
Okay. But if you look at the top here, it's not that value. A is times 10 to the, A times 10 power of 3 is equal to that value.
So it will be 10 to the negative 3.
Sorry? Yes, because A, oh dear, I need to check. Yeah, it should be A times 10 power of 3. If you look at that over here, is equals to 137.44. But that, you only need A because you're going to put A over in the equation here, in the polynomial equation. You only need A. So you don't need this part. So you got to bring it over to that side. So therefore, A is equal to 137.44 times 10 to the power negative 3. That's the reason. You want A only. Where are you going to put it over here?
Okay. Yeah. Thank you.
Okay, after this, nobody is going to ask the same question. Okay, that's good. If somebody asks again, it's going to be the third time I'm going to answer that. Okay, let's finish this. We sum it up. Okay, if let's look at the answer. Delta H1 10.542. Okay, that's 10.542. The second answer, the second step 28.85. The third step 24.66. Final step 0. So if you total it up, what will you get? When I did it, I get 64.05 kilojoules mole. Did you get the same answer, guys? Total it up, please.
Yes, I got 64.05.
Okay, thank you, Ikmal. So now, actually, what is the question asking for? It is asking for the specific enthalpy of that vapor. It is asking for the specific enthalpy of that vapor, which is this. specific enthalpy of that vapor. So, but why are we using the change in enthalpy? We are not. Are we what is required? We are asked for the specific enthalpy of the vapor. We give it a condition of 2 because the first condition is the liquid. The second vapor is 2. We gave it that nomenclature. So now, why are we using this? Our final answer is delta H instead of H2, specific enthalpy 2. What is the answer of enthalpy 2?
The same because each one is 0.
Okay, thank you. Delta H is equal to, if you look at the diagram that we have over here, okay, this is equal to 0. This is your enthalpy 2. So it should be delta H is equal to H2, your final condition, minus your first condition. But your first condition, you already said is equal to 0. So that is going to be the same as your overall change in enthalpy. So that is going to be the same answer. Thank you very much. 64.05 kilojoules per mole. This is how you calculate your enthalpy. When you don't have any data at all available, you have to look up the specific enthalpy. You have to look up the heat capacity, and you have to look at its boiling point, because there's a change of phase over here from liquid to gas. You need to know you need to know what equation to use. Based on this table, you need to know what equation to use based on what is happening. Change in pressure or change in temperature. You need to know that. And when there's a change of phase from liquid to vapor or vice versa, then you need to look up the boiling point at the value of the latent heat. The enthalpy change at vaporization. That is actually the latent heat of vaporization. You need to know that. Any question based on that example just now? Quite tricky, because you involve changing from liquid to gas. It changed from liquid to gas. Any question? If you don't understand anything, please ask, because this is very critical, your understanding here, in order for you to proceed further to do the calculation.
Doctor,
Yes.
I have other question.
Yes, please.
For this question, the substance, the liquid, turn from liquid to vapor, right?
Yes.
So what if the question says that the substance turn from liquid to solid? So is all the value going to be negative?
Okay. Thank you very much. Okay, now let's still look at n-hexane. Yeah, I'm going to use, let's see, I'm going to change that. Okay, now from liquid to solid is referred to, actually from solid to liquid is melting, isn't it? So that's the temperature of melting. That's the enthalpy change at melting. So that's the value. So now let's see. You were asking just now if it's from solid to liquid, then your enthalpy change.
No, doctor. The other way around.
Yeah, I know. Your enthalpy change will be this. Sorry, 13.03. That's the value. I need space. I need space. Let me erase that. This is, let me just write over here, from solid to liquid. From solid to liquid, that is your latent heat of melting. But if you are going back reverse direction, then what is that value? Negative. Delta H melting is equal to negative 13.03. And this occur at that temperature. Yeah, at that temperature. Minus 95.32, which is the melting temperature. So the change from solid to liquid, or from vice versa, liquid to solid, change at minus 95.32 degrees C, and the enthalpy change is the latent heat, enthalpy change at melting. So if you're from solid to liquid, this is what you're going to get as your delta H melting. But if it's from the other direction, from liquid to solid, then it will be negative. That's the only difference. Can you see? Can you see what I just discussed just now? Everything is crowded there.
Yeah, that's right.
Yes, good. Any other questions, guys?
Doctor,
Yes.
will delta H for vaporization or condense, will it always be provided?
You will look it up in Appendix B1. It will not be provided unless somehow the component is not in that appendix. Yeah, let's see whether I have one example that provided that. Let's see. This one example in your textbook, in fact, 831, if I'm not mistaken. Is it? No, not 831. 832 then. Can't remember. But somehow I know there is not this one. It must be a different example then. No, I can't remember. But there's one example whereby I have the temperature given. Can't remember which one. Not this one. Anyway, if it's not, if it's given, then it make life a lot easier for you guys. But if not given, the boiling point, the melting point, the change in enthalpy, then you have to look it up in Appendix B1. Your equation polynomial equation for integration is in Appendix B2. Where is it? Let me see. This is Appendix B2. There is Appendix B2. That is Appendix B2. Huh? Any other questions? Appendix B1 is where you have, let me see. Appendix B1 is where you have the boiling point, okay. We did this question just now. We did this. And hexane. We did this. We did this. How about looking at this? Any other question beside what has been asked? Any other question? Any other question, guys?
No, that's it.
No, good. Okay, let's look at this. Huh? You have, this is constant, you have, okay. This is a change in, you're going to ask for heat. You need to draw the diagram. You have 200 kilogram of nitric oxide. I'm not sure what's the symbol for nitric oxide. Anybody? We have the symbol NO, is it? Just O, NO, is it? 2? NO2, is it? Is there a 2 NO2 below it? I'm not sure.
N2O.
2, is it?
N2O.
NO2, is it? Or N2O?
N2O.
N2O. Okay, thank you. N2O. How to know? Look up in Appendix B2. Yeah? You're going to have it initially at 20 degrees C. Now you're going to heat up the same amount, 100 to 150 degrees C in a constant, whoa dear, constant volume vessel. It's a constant volume vessel. The heat capacity, when you're using at constant volume, you'll be looking at delta U. Okay? Whenever you do an energy balance, you must write your general equation. The energy equation, you must write it down. Either it's in a rate form or it's in just amount. You need to write it down. In this case, when that remind me. For the last chapter, whenever you solve any problem, write down the general equation. I saw that some of you guys, for question number 5, you did it wrongly. You did not use this equation, which is the general energy equation. That's one. Another thing that I need to point out is that you need to, whenever you cancel off, you need to give a reason. For example, delta E, there's no change in kinetic equals to 0. Why? No acceleration, for example, no acceleration. Or you can just say no change in velocity. No change in velocity. Yeah, you can say that. No change in velocity. You need to specify, or else you will lose marks there. Yeah, no change in pressure. No change in pressure. So not pressure. Potential energy. Why? Because no change in elevation. No change in elevation. You need to write that down. Now, what else? Work. Work equals to 0. Why? No moving parts. There's no turbine. There's no pump. So no moving parts. That's why it's 0. You need to write it down. Because if you do not write down, you will lose marks there. Okay, now, in this question, if you look at the equation over here, you end up with delta U. Okay? You cancel off already kinetic energy, potential energy, work. You end up with the change of heat is equal to change in, heat is equal to change in internal energy. So now, internal energy, if you look back at our here, oops, where is that table just now? Okay, this is the table that I want. Let me erase anything that I don't need again. Okay, internal energy. That's internal energy. That's internal energy. That's internal energy. That's internal energy. Now, for that example just now, what happened actually? For that example, 831. What happened over here? What changed?
We have a constant volume, no change.
Constant volume? What changed then? The volume is constant.
Temperature.
Temperature change. There is a temperature change. For what? Is it gas or liquid?
This is gas.
It's gas. Okay. So now let's go back to our table. Is gas, we're looking at gas. Is constant change in temperature. So what is the equation for delta U or our internal energy, change in internal energy? What is the equation to get your internal energy change? Anybody?
Del B equals CV del T.
Okay. That's the equation. Yeah. We need to integrate CV instead of CP. It's constant volume. Yes, Ibrahim?
I mean, it's T2 minus T1. CV T2 minus T1.
T2 minus T1. Okay.
CV, yeah.
It's not written over here. There should be T1 here. Okay. T1 to T2 integrate CV with respect to temperature. So now let's go back to our example. So that is equals to, from T1, what is T1? That's T1. That is T2. Yeah. So going from 20 degrees C to 150 degrees C, and your CV with respect to temperature DT, and your CV is given over here. Yeah, your CV is given over there. So now what you have to do is just, and it's already stated here that your temperature must be having a unit of degree C. So just fine. So now what you have to do is just calculate your Q is equal to delta U. There's no, I'm sorry guys, there's no rate here. Why no rate? Because just 20, isn't it? So it's just delta U. No, there's no dot over there. There's no dot. I need to erase that. There's no dot. Yeah. So there's no dot because it's not per unit time. It's just 200 kilograms. That will be from 20 degrees C to 150 degrees C. Copy your equation, just jot down the equation as given. Minus 4P with respect to dt. Look at the unit, guys. I need to point this out. Look at the unit. Okay? The unit is different from what we have done so far. The unit is kilojoules per kilogram per degree C. The one that we have done so far is mole. Kilojoules per mole per degree C. That is the one from appendix B2. But this is the given unit for this example, which is per kilogram. So take note of the unit. Yeah, so now let's do the integration. What's the answer, guys? You have your calculator. What's the answer? Anybody give me an answer? You should. Sorry?
I got 111.27.
Sorry, can you repeat that again?
111.27.
27.
I got different answer.
Different answer. Okay, what did you get, Ayman?
121.56.
6. Okay, now I have two answers here, guys. The rest of you guys.
The second one is
Second one.
The second one is correct?
Yeah, I think so.
You think so, Ibrahim? Redo your calculation. Yes, anybody? Give me a different any different answer. Which one is the correct answer of these two, of the two answers given?
I got 1.56.
121.56. Okay, Agatin, thank you. So this is the wrong answer. Yeah, this is the wrong answer. Okay. So now let's look at the unit just now. Is kilojoules per kilogram. Kilojoules per kilogram. And that is per kilogram. How many kilogram do we have? We have 200 kilogram. So in order to get, that is specific, guys. That's specific. And you have to remember, that is specific. Let's go back. I need to point this out to you guys before we proceed. This is specific change in internal energy. Specific. Yeah, specific change in internal energy. So I should not write it as such. I should not write it as Q. Okay, I should not write it as Q. Why? Because it's only specific energy. Only specific internal energy. Q, if you look at here, there's no specific sign on top of the cap. There's no cap sign, isn't it? On top of the key, on top of the U, there's no cap sign on top of delta U. So that means, if you want to calculate Q, delta U is equals to out, not out, because it's a closed system. It's not out, not out. It should be final, which is MU specific minus initial MU specific. Since it's only one, you only have one mass, you take it out. Now you have U final. Don't need the summation now because there's not there's not a multiply of. That will be final minus specific initial. And that is going to be M delta U specific, isn't it? Isn't it, guys? This change is equal to delta U specific. And what is that? That's the value. Oh, okay, it's quite slow. So what is your mass? 200. Yeah, so 200 kilogram. What is your change in internal energy? 121.56 kilojoules per kilogram. Cancel the kilogram, you will get your final answer. I don't have the answer, but let's see. Let's look at the question. What is the answer? 24,300 kilojoules. Let's see. Is it 24,300 kilojoules? Or is this round off values?
Yes.
Exactly?
No.
No.
312.
312. Okay. So that means it's round off then. Kilojoules. That's how you get your final heat. When you heat up 200 kilogram of that nitric oxide, that's going to be 24,312 kilojoules. When you heat it up 200 kilogram from 20 degrees C to 150 degrees C, this is easy. Why are we not doing any hypothetical path here? Why are we not doing a hypothetical path here?
We can't do it without it.
Why?
Only change in temperature.
Yes, thank you, Ayman. Because there's only change of temperature. You know, there's only one change. You need to draw the hypothetical path, because when it involves change in pressure, when it involves change in temperature, or change in phase, then you have the hypothetical path that you need to do. But in this case, there's only one change, which is the temperature. So you don't need to really draw the hypothetical path. You just get the equation from the table. Any questions? In this case,
Doctor,
yes.
here, if it's a specified change in pressure, if I ignored it completely, will I get the 4 mark? Because like ΔU for pressure is independent.
You mean if the pressure at P1 is different from the pressure at P2?
Yes, but both are gases. And
Okay. That is the same as the first example I did, remember? I did one example. Let me see. This example, is it? Yes. You have change of, it's liquid. There's no change in the phase. You have just both liquid, and then you only need the change of temperature. This is a change of temperature. Then a change of pressure. You only have change of temperature and pressure.
Yes, I mean, but there they want the change in internal energy, and it doesn't depend on pressure. So should I ignore it?
Okay, let's go back to our table. Change in pressure for gas. The internal energy is, sorry?
Internal energy.
Yeah, internal energy is 0 for gas.
And liquid as well.
Liquid also, yes.
So I can ignore it completely.
Yes. Yeah, don't just write down change of internal energy equals to 0. You need to write it down. You cannot just completely ignore it without writing anything. Yeah. So that's it. You need to write it down.
Okay, that's it. Thank you.
Okay, welcome, Ayman. Any other questions? When there's only a change of temperature, it's the easiest. It's the easiest when there's only a change of pressure. Temperature. Let's see. Anything that have 833. That's 833. In this example, only a change of temperature. Change of temperature. Okay, let's do this. This is interesting. You have two ways of doing it. One using table B2, the other one table B8. The same question, calculate Q. Same question, calculate Q. Okay, let's do this. We're going to do the first part first. Draw the diagram. Oh, guys, I forgot. Please, next time, what is your basis? What is your reference state?
Basis 200 kilogram.
Okay, good. Now, reference state?
Reference state.
What is the reference state?
20 Celsius.
Sorry? What's the reference state?
Doctor, maybe 1 ATM, 25 Celsius?
25? Are you sure?
20
Let's go back. Let's go back. Let's go back. Yeah, let's go back. Sorry. When you do this, yeah, you are starting. That means this is equal to U2 minus U1, right? Isn't it? Change in delta U. Yeah? So if you assume that U1 is equal to 0, that becomes U2, isn't it? So what is your reference state?
20 Celsius.
20 degrees Celsius. That means N metric oxide gas, you write it down, 20 degrees C, assuming that is at 1 atm. Write it down. Okay? Your reference state is Nitric oxide gas, 20 degrees C, 1 atm, because that's where you start your calculation from. You integrate it from that temperature. Because there's only one change in temperature. You don't need a hypothetical path here. I'm having difficulty pronouncing it. Your reference state is, you could choose your first condition or your second condition. But if you choose your second condition, then you integrate from the 150 to 20. Where you start integrating is normally, in this case, because there's no other thing that is changing, only temperature. So your reference state will be that first temperature where you start. Okay, guys? Okay, now let's go back to that 833. Not sure whether we have enough time to do this, but just maybe we can do part of it. We continue maybe next week. Okay, now, basis. Basis 15 kilogram mole per minute of A is cooled from 430 degrees C to 100 degrees C. So what is your basis?
15 kilomole per minute.
Of A. Okay, yes. That's your basis. What is your reference state? What is your reference state?
On the table there, up.
If you say, for example, if you're using table B2, what is your reference state? Guys, your reference state can be the inlet or the outlet, either one. If it's not specified, because this is table B2, you're only given the CP equation. Okay? Because you're only given the CP equation, you don't have any data, then your reference state could be the inlet or the outlet. It's a matter of choice. You want inlet or outlet. If you are going to start from inlet, then you're going to specify A at 430 degrees C and 1 atm. That is your inlet. Or you could do the outlet, either one. But remember, if you integrate, your starting point is where your reference state is. So your first temperature at the bottom of the integration will be your reference state. Now that is when you using a table B2, because you don't have any data. But if you're using this table, if you're using B8, you have to follow the same reference state as given. But in our case, you have to write down A at a pressure of 1 atm, temperature 25 degrees C. Okay, let me repeat myself. If you're going to get your enthalpy from any sources that is already, that you can get it directly from that table, your reference state must be the same as that in the table. For this case, your reference state should be where the enthalpy is 0. Where the enthalpy is 0. That is your reference state. That means at that temperature, at that pressure. But if you're going to get it from your table B2, whereby you don't have the data directly given, but you have to do the integration, then you have to choose your own reference state. Is it going to be the inlet or the outlet? Okay, I'm not going to proceed here, but what I want to show you guys is the step to do it. Not really the step, the procedure to do energy balance. Yeah, I'm going to show you guys the slide. I'm using PDF right now. I'm not using my PowerPoint because I find this is far easier than whereby I can write on my slide. Okay, this is the procedure. Okay, guys. First, write your basis, of course. Don't forget your basis. Don't forget your basis. Okay, do your energy material balance. Secondly, decide, are you looking at closed or open system? If you're looking at closed system, that's the equation. If you're looking at open system, that's the equation. You need to write the full equation. Same thing as for chapter 7. You need to write the full system. Do not use delta H is equal to Cp delta T. That is in thermodynamic. we are looking at energy balance. Okay, so you need to write the full general equation. Whenever you cancel anything, justify why is it cancelled off. Okay. Next, reference state. Reference state, you need to specify what phase is it, liquid, gas, solid, what temperature is it at, what pressure is it at. Normally, you can choose inlet or outlet. It's a matter of choice if your data is not available. But if your data is given, whereby you get it directly from, for example, steam table, then use the same reference state as that of the steam table. For example, just now, table B8, the reference state is given inside that table. It is stated that it is, for example, we are looking at A, so you write down A, gas, at 25 degrees C and 1 atm. You have to write it down according to where you get your source of data from. Okay, your reference state must be the same as the table that you get your data from. If there's no data available, for example, you're getting it from your CP, then you choose. You want it to be inlet or outlet. It's up to you. So if you choose your inlet, then when you integrate, okay, H is equal to, this will be your, if you choose your inlet as your reference, then it will be inlet as the bottom temperature. Then that will be your outlet. Then Cp dt. So that will be the same as your reference state. Okay. Next, once you have already decide what is your reference state, you need to do a table in this form, just like what I have done in chapter 7. You need to do in this format. You need to tabulate your table, just like what I have done in chapter 7. Okay, but based on what we have done today, I did not draw the table because you only have one substance. When you have only one substance, you don't need to do the table because whenever you have more than one, then you do the table. Now, after you have get all the values for your enthalpy, you need to either get the internal energy, the enthalpy, and then you cancel whether work is going to be cancelled, potential energy is going to be cancelled, or drop off from the equation. Then you solve the unknown that is required. So this is the procedure. I have followed that actually when we did the example 831. I do not solve for the material balance because we know inlet is the same as outlet. We don't need to do the material balance. We did write down the basis. Okay? We write down the reference state, which is the inlet. I write down the equation for the constant volume, which is a closed system. This is a closed system. So you need to write down your equation. After that, you write down your enthalpy, which is this for the first condition, which is 0. And this is your enthalpy for your second condition, which is your outlet. Okay, so this is how you do your energy balance. So you end up with the final equation, that's final answer. You cancel off whatever term that need to be dropped off from the equation. Write down why it is cancelled off, why it is being dropped off, why is it 0. You need to write it down. Guys, any questions? I'm not going to solve that example because I don't think we have enough time actually. So we're going to do that next week, inshallah. Any questions, guys? So far, any question, anything? Sorry?
No, that's it.
No. Okay, thank you, Arif. Besides Arif, anybody else? Is everything fine with you guys?
Doctor.
Yes.
Can I ask you about the test?
Yes. Yes, Omar.
Yes, Omar. How many decimal points should I take for my final answer?
Sometimes they specify it inside the question itself. Normally, your I don't know, based on your material balance, is it being specified how many decimal places you need to place? You need to do?
No.
No. Okay. You can do 3 decimal places or 2 decimal places. I think 3 would be fine.
Okay, yes, thank you.
Okay. And the final answer, you need to box it. Remember to box your final answer.
Yes.
Yeah. And remember the basis, remember the reference state. Most students forget it. When I look at the assignment, you might remember the basis, but you forget about the reference state. You please write the general equation in full, and then you cancel it off. What term need to be dropped off? Anything else besides that two questions? I mean, besides the question on the test, anything else? Anything you need to know about the question? Well, there will be 3 questions. 2 of them will be on closed system and one of it closed system, the other is open system, and one of it is going to be mechanical energy balance. As always, you have that stream flowing in, you have the you have the pipe, maybe change in velocity, maybe something like that. Yeah. So make sure that everybody can access the e-learning, because the question is coming from e-learning. Be ready at least 10 minutes before. Anything else about anything that we have covered today or the test itself? I have already, look at your, no, I haven't finished marking it yet. I just look at the question 5 actually. And please do not solve it using Cp delta T. This is not thermal, this is energy balance. You need to use the general energy balance equation. And remember your reference state. Do not put steam/water. It cannot be both. It has to be only one. It either liquid water. If you're looking at the steam table, it must be liquid water. Any other question, guys? Before we call it for we quit for today.
Doctor.
Yes, Aiman.
So for the test, there will not be any question requires Cp delta T to solve.
Cp delta T, no.
Okay,
you only started Cp delta T when you are doing integration, which is this chapter. Yeah.
Right, Doctor.
Good, thank you. Anything else?
Doctor,
Yes.
I have a question, related to the back of the book, question 7.32.
You're looking at appendix what? Sorry, not appendix. You're looking at the 3rd edition or the 4th edition?
3rd edition.
Okay, what's the question number?
The question 7.32, the last question.
7.32.
Yes, the last problem question.
Hold on, let me look at my textbook. 7.3. Okay, 7.32. Okay, this is wet steam, is it?
Yeah, water from a reservoir passes over a dam.
Oh.
Through a turbine.
I got a different question. 7.32. Mine is steam produced in a boiler. What's the question just now?
Water from a reservoir passes over a dam through a turbine discharge.
Oh dear, my numbering of question is not the same as yours.
In the, I think, are you using the 3rd edition, right?
Yes.
Yeah, I'm using the same.
Yeah, but somehow the water from reservoir. Okay, mine is 7.56.
Oh, okay.
Okay, this must be an old 3rd edition. Okay, water from a reservoir passes over a dam through a turbine and discharge from a. Okay.
Yeah, this question, they didn't specify, they didn't give us any of the, the velocity, but then they just gave us, the turbine delivers, the work that turbine delivers. And then from there, they asked us to calculate the mass, the volumetric flow rate, in meter cube per minute. But then we don't have even the mass flow rate. Or, so I tried to check few videos, but then there was some equations that I've never seen before.
Okay, I will look at it because I'm not sure whether I can give you the. I'm not sure, I don't have the solution here, but what I can say, this look like similar like what we have discussed in one of the example last week, isn't it?
Yes, it's similar, but only the problem is that some informations are missing compared. Before they used to give us one of the velocities, or no, they give us the mass flow rate.
Okay, let me see the diagram. Okay, there's no diagram here. What I can say is water from a reservoir passes over a dam. Okay, you need to use one of the velocity on the surface of the water, which is equal to 0. Yeah, one of the velocity will be 0 on the surface
Yes.
of the water.
Yes, right.
Yep. And you need to calculate the second velocity coming out from the pipe line, the outlet pipe, the discharge velocity. You need to calculate that. U2.
Okay. Mm-hmm.
Okay? After you have calculated that, then based on the cross-sectional area of your pipe, then you should be able to get the volumetric flow rate per minute. Okay? Because you have velocity. Velocity is meter per second. If you multiply it with the cross-sectional area, you will get meter cubic per, your velocity is going to be meter per minute. And if you multiply that with the cross-sectional area of your pipe, you will get meter cubic per minute. So you need to find the discharge velocity, then multiply it with the cross-sectional area. So your basis will be the volumetric flow rate that you calculated. Okay, it's the same, almost the same like the example that we did.
All right. All right.
Okay, good. Any other questions? It's already, yes.
For question 4 in the assignment, here, part B, it asks for del U.
I don't have the, sorry, hold on. Let me try to find the question. I'm not sure. What is the question? If you can maybe share with us. Let me see. Let me see. Where is the question? Let me try to get my question first. It's in my, let me see. I don't have the question here. Okay, let me try to look at some of your questions. Okay. Okay, question number, oh dear.
Can I share it, Doctor?
Yes, please. Can you share?
Okay, sure. I think this one.
Okay.
So for part B, it asks for the change in internal energy. But here in the question, it says that there is Wn due to state resulting work. So the only way to calculate del U is by using CV. Or should we assume there is no W and only calculate the energy balance equation using Q and del U?
Okay, hold on. The question said 5 kilogram of air from 50 degrees C at 5 100 kilopascal going to be changed, or you're going to find the final temperature. Okay, what's the question for change in internal energy? You need to use the, oh dear. Why are you guys using CV?
Because, Doctor, if I write the energy balance equation, I'll have two variables. The Wn, which I don't know, and del U. Q is mentioned, but I don't know neither Wn or del U. So the only way is to solve it using CV. So is it okay?
But you know the final pressure, right? The final temperature, right?
Temperature is calculated in part A.
You already got that, right?
Yes.
Okay, now, look, if you're going to use the table B8, you use this AA, okay? That is enthalpy, sorry. This is what? Close in a container, okay? Don't have internal energy, don't have work.
Yes. Some of my friends assume that work is 0. We can ignore it for this part and then recalculate it.
No. That's not the way to do it. No, that's not the way. Based on the temperature that you know, you can get your internal energy. That's not the way to do it. I'll get back to you guys on that because I don't have the solution with me. Let me see. I'm looking at somebody else's solution right now based on your assignment. Let me see. Number 4. By right, based on the temperature, you should know what's your internal energy change.
Yes.
Okay. Okay, what you can do is Right now I got somebody's problem here, somebody's solution here. Okay, using appendix B8. Okay, this person is using appendix B8. She calculated H. Then from H, calculate U. Understand? Using H equals to U plus PV. Okay, you have the pressure, you have the volume.
Okay.
The volume.
The volume. The volume is constant, actually.
So if the volume is constant, that means that cancel off, isn't it?
Yes. Yeah. So V delta V.
So it becomes. Somebody did this using. Let me see. Delta U.
What answer did he get?
For which one? For the second one? I'm not sure whether this is correct, but that person managed to get 32.71.
I got 3,478 kilojoules.
Okay, I tell you what, Ayman, because the time is almost 4 o'clock. I will try to get my solution and post it in WhatsApp. Okay?
Yes.
Yeah, good. Any other things besides that? Anything else?
Thank you, Doctor.
Thank you. Okay, that's it. I will post it in WhatsApp. I will try to get the solution because I'm not sure this person whether her answer is correct. So I can't say because I haven't looked at question 4 yet. I just looked at question 5. Okay. So thank you guys for coming.
Okay, Dr.
Yes.
What if I use the thermodynamic property table? There is a table for air.
Yeah. If you can do that, that would make life a lot easier because you know the temperature already, isn't it?
Yes.
Because if you use the thermodynamic table, you know the temperature, then you will directly get it. But I'm not sure whether the person asking it asks you to do it that way or not. That's another different issue because maybe they wanted you to calculate it using the the equation U is equals to H is equals to U plus PV. Might be one of the way to solve it. But if you're using the thermodynamic table, then obviously it's just getting the directly from that table. Then you have to specify where you get that from. You need to say, okay, from the thermodynamic table. Okay. Hey guys.
All right. Okay.
Yeah. So thank you very much. Already 4 o'clock. For those that haven't slide in, I'm not sure. Do you still need this QR code before I deactivate it? How many participants do we have actually?
Doctor, it still shows 0 out of 37.
Sorry?
I mean, it still shows like.
Yeah, that's why I was asking just now. Why is it 0 out of 37? How come? How come? I don't know why. Okay.
Prof, can you wait while I need to scan because I didn't scan earlier.
Okay. Those who need to scan, please scan. But I'm just surprised the attendance is 0 out of 37. But I know that you guys did scan it because this obviously is listed here. Okay. Your names are listed there. I know you scan, but the problem is why is the attendance 0? That's my question. Okay, for those we are done for today. Thank you very much for attending this lecture. If I'll just like I promise, I will get you back to you guys on question number 4, and I look it up. I will give it to you guys in WhatsApp. Okay, guys, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Welcome.
Thank you.
Thank you.